Welcome to perhaps the final lecture on photoelectrochemical cells. In this lecture, we will talk about the different configurations that have been creatively attempted and to overcome the many challenges of photoelectrochemical systems. So much of the material is from this very insightful review paper by Gretzel. If you're going to be researching in this area, so you should surely read this manuscript. Um, Other parts of this lecture is from the textbook for this course. So an important paper in this field is this paper by Fujishima and Honda in 1972. So that's a long time ago, more than 50 years ago. Um, it was presented uh, during the time where there was a lot of crisis in obtaining energy solutions due to variety of political forces. There was energy crisis. So there were other methods than the hydrocarbon methods. Other than the hydrocarbon methods, there were methods based on renewable energy that were attempted to provide a solution for large scale energy. So this work, the experiment looked fairly simple, right? So look at the setup. This is fairly uh, simple setup, and it's at room temperature, just water, and titanium dioxide is readily available, and so on. Okay, so the in this setup, uh, there is sunlight in this electrode. Sunlight is absorbed by this electrode. In this on this electrode electrolyte interface, oxygen evolution occurs. While oxygen evolution occurs, two protons is released, and these two protons get reduced in this electrode, at this electrode electrolyte interface. Two protons combines with two electrons, giving rise to hydrogen. So this is the way to convert solar energy to fuels, right? So both oxygen and hydrogen are valuable chemicals in the chemical industry. In addition, hydrogen can be supplied to uh, a fuel cell or to an internal combustion engine to generate either electrical energy in the case of fuel cell or mechanical power in the case of internal combustion engine. So this looks great, right? So let's understand why, despite more than 50 years, why this approach has not resulted in a practical technology. So looking at this in certain detail, uh, when semiconductor absorbs light, it generates hole and electron. Water splits into oxygen, and the two electrons released combine with this hole, right? So there is an electron transfer from the electrolyte to the semiconductor, and this electron fills the hole in the valence band edges. And then this electron goes across the wire uh, and then gets to the counter electrode, wherein this reaction occurs, right? So that's what we see. We have already discussed quite a bit on why there is semi band bending at the semiconductor electrolyte interface and why it is critical for electron hole separation. So let us see the why I have stated this as hope and hype. Okay, so every few years there is some sudden, what appears to be a sudden progress breakthrough, but in time, uh, you see that that approach will also not succeed. That's why even after 50 years, uh, whether we would be able to get a large scale technology using this approach is not very clear. So what are some of the constraints? So first, we want to split water, it's an into oxygen and hydrogen. It's an endothermic reaction, right? So minimum 1.23 volts is required, right? So if you want to um, split water in a water electrolyzer, the bias, minimum bias based on thermodynamics, you need to apply is about 1.23. In addition to this minimum thermodynamically computed bias, there are other O potentials, anodic O potential, cathodic O potential, ohmic O potential, and other systems oriented losses. All these things, when added up together, the minimal potential that you need to have is about 1.6, right? So that's what is seen in an electrolyzer. If you want to get appreciable current in a water electrolyzer, you need to have 1.6 volts. um, the potential that can be generated in this kind of a setup can be correlated to the band gap of a semiconductor. So that is, if I uh, try to compute the photo potential is correlated to the valence band edge and the conduction band edge. So if you want to get at least 1.6 volts, the minimum band gap that is needed for the semiconductor that is utilized in the system should be about 1.6. So this right away excludes the most common semiconductor, silicon, which has a band gap of 1.1. Not only it is because of uh, the band gap, just having silicon is not productive. It is also that when silicon, when it's exposed to an electrolyte uh, atmosphere, it the surface gets oxidized and it forms silica at the surface, which is a very insulating layer. So both reasons contribute to not using silicon, at least just a plain single junction silicon. But silicon can be used in other ways in the system, but we are not going to that. So if you want to use semiconductors beyond 1.5, 1.6 band gap, there are 1.6 EV band gap, there are uh, choices available to you. Okay, so there are challenges based on band gap. And let's look at other challenges. So the electron has to be transferred from water to valence band edge. Uh, so if you look at the put redox level of this system, that is H2O2, it is somewhere here. So this energy level should be above the energy level of the valence band edges, right? So that because you are transferring electron from this redox level to the valence band edges. So there are some semiconductors uh, which can be utilized which satisfy this constraint, and some of the semiconductors cannot be used because of this constraint. And then this energy level at the counter electrode is can be correlated to in some measure by the conduction band edge, right? Because the electron from here gets to the counter electrode. From that counter electrode, you are going to be transferring it to proton, right? So if you look at the that redox level, let's say that is over here. So the uh, conduction band edges of the semiconductor that is utilized should be higher than this redox level, because electron transfer occurs from the conduction band edge. The conduction band edge goes to the counter electrode. From there, you are transferring the electron to the redox level. So some of the semiconductors satisfy this condition and some others do not satisfy this condition. There is some flexibility based on pH and so on, how you can move around, but these are dominant constraints. Band gap is a dominant constraint. It should be above 1.6. And then the constraints on band edges with respect to redox level has to be also satisfied. So if this level is much higher than the valence band edge, the driving force for electron transfer is much greater. If the this difference is very less, then the driving force for electron transfer, uh, this electron transfer is lesser. Likewise, if the conduction band edge is much higher than this redox level, the driving force for electron transfer is greater. If it is not well separated, the thermodynamic driving force and hence the kinetics will also be challenging. Let's move on. The next constraint is that constraints on catalysis. Uh, okay, so this is not a easy reaction. Okay, so as opposed to this reaction, that is, you have bare proton or hydrated proton in the solution. Um, Hydrated proton uh, combining with electron to form hydrogen is not that challenging a reaction. The nature of catalyst that needs to be utilized is not uh, very challenging in this case, but uh, to an extent, effective catalyst has to be utilized here, because the catalyst, if you use a very simple catalyst, if supposing it gets oxidized in the solution, that will lead to problem. So there are some aspects of catalysis, constraints based on catalysis at the counter electrode. But the more challenging reaction is this reaction. Breaking water molecule into oxygen and proton. That is not at all a trivial reaction. So fairly expensive surface, uh, um, electrocatalysts have to be utilized for driving this reaction at reasonable rates. So surface electrocatalysis, especially of this reaction, is a big challenge. In addition, a great challenge in this system is corrosion. Um, Water itself is might lead to some surface reaction, but when the water is in, let's say, acidic condition, the that condition is fairly corrosive. Just go and look back at the lectures in pore bear diagram and corrosion to understand this point more clearly. So, why do you need either acidic or basic medium? First, if you don't use uh, acidic or basic pH, the ohmic resistance in the electrolyte is significant. So you want to be having, let's say, acidic pH for effective transport of ions in the electrolyte. So such an atmosphere has a lot of issues regarding corrosion. So many of the semiconductors that seem promising in terms of band gap, in terms of band edges, are not stable in this medium. So that is another grand challenge. One semiconductor that is very very stable, uh, let's say titanium dioxide, that was the semiconductor that was utilized in Fujishima Honda manuscript in 1972. That has a band gap of 3.2, right? So in terms of solar photon absorption, that's not very good. Uh, we have discussed the constraints on solar photon absorption in an earlier lecture. So ideally, if you have, let's say, 2.2 band semiconductor with the band gap of 2.2, let's say iron oxide, that is very productive. A lot of work has been done with iron oxide because it's inexpensive. Not only it's inexpensive, it's not toxic. It has a right band gap to capture a lot of uh, solar photons. Unlike Fe2O3, titanium dioxide is as a significant band gap, but it is very stable. Fe2O3 is also stable, but its electronic properties is not that great. Okay, so it's not a good uh, hole conductor and electronic conductor. The recombination rates is also significant in Fe2O3. Titanium dioxide does possess a lot of advantages, especially from it being very stable, non-toxic, and fairly inexpensive. So, creative approach again was developed by Gretzel. This is called dye-sensitized solar cell. Instead of having TiO2 absorb solar photon, dye was loaded onto porous TiO2. Let's say either chemically bound dye or the dye is bound to porous TiO2. The solar absorption is not done by TiO2, but it is done by the dye. So why do you need porous TiO2? It increases the amount of surface area that is available. Therefore, more uh, dye can be loaded, uh, and there is greater surface available for the reaction. So the optical capture, the solar light energy capture is not done by the semiconductor, but it is done by the dye. So there is injection of the excited carrier, charge carriers into the semiconductor, and there is a redox couple which can get oxidized, reduced. Okay, so this has been attempted, but this also has challenges. That these dyes can be expensive, and the dyes might not be stable, right? So sometimes the bond between the dye and the semiconductor itself breaks. So this looked promising, but this has also not resulted in a commercial product. So this constraint of band edges has been addressed by um, tandem cell. Okay, so for example, here you have tungsten oxide. So the valence band edge of tungsten oxide is well suited for doing one of the reaction, let's say oxygen evolution, and it has a good band gap, right? It's a band gap of 2.6, which is good. It's not too high, much more than 1.6 that is required. And this is very stable. Tungsten oxide is relatively non-toxic and inexpensive, relatively inexpensive. So unfortunately, the conduction band edge is below this redox level. So there is a constraint with respect to reducing protons to form hydrogen. So instead of that, you have a tandem cell. That means tandem means two things are combined together. So if you absorb two photons, there is uh, this system, okay, which has a different HOMO-LUMO. There is highest occupied molecular orbital, lowest unoccupied molecular orbital. Uh, so this uh, will capture light. There'll be excitation here. There'll be excitation here. This electron will go and quench these holes. And effectively, the reduction occurs with this band edge position or the electronic level. So you do oxygen evolution with this band edge position, you do hydrogen evolution with this electronic level. So this has also been attempted, explored significantly, but again, this has also not resulted in a commercial large-scale technology. Other approach involving two photoelectrodes, a photoanode that generates oxygen and photocathode that generates hydrogen has also been attempted. This also has a lot of advantages, but in eventually this has also not generated any commercial technology. If you notice the band edges, band bending is different here. This is an N-type semiconductor. Here you'll have P-type semiconductor. So all the issues which we dealt with band bending has to be put together to understand this kind of a system. This also looked promising, but eventually did not give rise to a large-scale commercial technology. Uh, if you think about the potential at which you need to be operating, so it is similar to much of the analysis we have made in many other electrochemical system. For example, if you have high potential, that is, let's say, an open circuit potential, you have large voltage that is available to you. For example, supposing you are using photoelectrochemical system to convert solar energy to electrical power. So at uh, when you have open circuit potential, of course, there's no current. When you keep increasing the current density, the potential drops significantly due to variety of overpotentials. So what you try to do is that you operate in some in between current densities and potential such that your power that can be obtained is a maximum. So maximum power is from this kind of a system can be obtained at some in between voltage and current density. So we can also talk about electrical efficiencies, right? So what is incident solar power? That it's about 1 kilowatt per meter squared on, let's say, hot sunny day, the middle of the afternoon. This is called solar insolation, INSOLATION. So this again varies from place to place depending upon the latitude and longitude of the place and the time of the day, right? So if you even if you consider solar energy conversion, probably you can utilize the device for about 6 hours a day. That is another disadvantage, right? In any case, the efficiency can be defined in the following manner, right? So you have input power in the denominator and the numerator output electrical power. So if you're thinking about photoelectrochemical solar to hydrogen conversion, the target efficiency is about 6 to 7%. Why do you say that? Because if you take electrolyzers, the electrolyzer become fairly efficient. It's about 60 to 70% efficient. And if you have an inexpensive solar cell, let's say amorphous solar cell, that is about 10% efficient. So 10% times 60 to 70%, the photoelectrochemical system should have 7% efficiency. So these are target efficiencies. And if you want to have a large area device, you have to get such a photoelectrochemical system which 6 to 7% efficiency using inexpensive material. You should avoid using platinum and inexpensive materials. So that's a grand challenge, right? So another indicator of efficiency is so-called fill factor. This is at maximum power. What is the IV divided by short circuit current and open circuit voltage? These all we get from semiconductor solar cell community. These efficiency measures have been developed from solar cell community. So as opposed to photoelectrochemical solar cells or photoelectrochemical hydrogen generation, solar cells have become a reality, right? So both of these systems started around the same time, right? But um, silicon solar cells have become a large-scale technology all around the globe, right? So this approach, that is the electrochemical approach to solar energy conversion, has not taken off. Overall, what are the topics which we have addressed? We looked at many properties of semiconductor, especially you should get used to the notion of Fermi level, what it really means, what is the role of majority carriers, minority carriers in N-type, P-type semiconductor, how, how is band bending achieved in a semiconductor electrolyte interface, and why is band bending important? It is very important for separating the electron hole pair that is generated upon light absorption. You should understand the dark characteristic, what happens under forward bias and reverse bias. That is the current characteristic when there is no light in a semiconductor electrolyte interface. Then you should understand the photocurrent characteristic uh, due to what carriers, that is, whether the photocurrent is due to majority or minority carriers, that should be clear. And the underlying reason for minority carriers being the photocurrent contributors should also be clear. And we also looked at different photoelectrochemical configuration and constraints. The fundamental electrochemistry of this system is really beautiful. A lot of exquisite um, um, electrochemistry enriching science is available. Why this system is so um, alluring is because nature does it this way, right? If you take a leaf, leaf, it captures solar energy and drives uh, an endothermic reaction, CO2 and H2 to form sugars and so on, right? So that's the way nature works, but nature does it at not a great efficiency and the rates are very slow. But if you want an industrial process, you want to be very efficient, um, and it should the rates should also be significant. So a lot of attempts have been made into developing a practical artificial leaf technology, but there has been a lot of hype, hope in this uh, area. So it is we still hope as electrochemists that one day we would have a practical large scale technology from this uh, field that is given exquisite science. With this, let us close this topic. Thank you.